Hi, this is Professor Stugard, and in this lesson we're going to talk about how do we find the surface area of our functions of two variables using, well, integrals. Now before we get to that, I want to go back and review quickly arc length because we're going to see that the formula for arc length is actually going to be related to our formula for surface area because, well, really they are kind of looking at the same idea. Arc length is, again, a measure of space in 2 dimensions, and surface area is going to be a measure of space in our 3 dimensions. And so, again, if you remember back to your previous lessons, we find the arc length of a curve by, well, this formula. Our arc length L is the integral from a to b, that being the interval of our function, and then the square root of 1 plus our derivative squared, and then dx. Now we also looked at arc length in terms of our parametric functions, and so if I have a parametric function in R2 given by x of t and y of t, and then t is bounded between alpha and beta, because again, typically we do bound our parametric functions in between alpha and beta instead of just a and b, then, well, the arc length is that integral from alpha to beta, and then the square root of dx dt squared plus dy dt squared dt. And the reason I'm showing this is because, well, this is the Pythagorean theorem. We find arc length by doing the Pythagorean theorem. We're really just making a right triangle out of our arc, slicing it up, and, well, applying the Pythagorean theorem. And so when we find surface area, what we're actually finding here is going to be the value if I take my surface and I chop up my surface into infinitely many infinitesimally small tangent planes. I can then add up the area of each of these tiny little tangent planes, and that will give me my surface area. Now when we do this process and we chop our surface up into infinitesimally small tangent planes, we call those infinitesimally small tangent planes patches. And we're going to actually come back to and revisit this idea a little bit later on in our next chapter when we talk more about what a surface integral is, because we're going to have to do surface integrals which actually involve surface area. So we'll talk about this again and where the formula comes from in a little bit more depth, but hopefully you can kind of see that again. If we're making our tangent planes, those involve our partials, and, well, then we also know that the area is going to involve cross products, and you can actually probably get a decent idea of how to derive this yourself. But for now, we're just going to focus on what the formula is. And again, hopefully we can kind of see the familiarities with our arc length, but for our formula for the surface area, for a function z equals f of xy, and again, this part is actually quite important. We need to make sure that our function has z on one side and just x's and y's on the other side. And then our formula for the surface area is going to be the double integral over my region D, then the square root of 1 plus, and then my partial with respect to x squared plus my partial with respect to y squared. And again, hopefully we can see the similarities there with the arc length formula. And both of these expressions are exactly the same. It depends on which way you prefer to write your partials, whether you prefer f partial x or the partial z partial x, and the, well, f partial y or the partial z partial y. Again, they mean the exact same thing. So again, whichever formula you feel more comfortable committing to memory is fine. So let's take a look at some examples and see how we actually use this. So let's say I want to find the surface area of the plane 2x plus 3y plus 6z equals 9, which is bounded in the first octant. Now, just like before, the first step is to make sure we understand our region D. What is the region we're going to be integrating over? That needs to be our first step. So when I say I'm bounded in the first octant, that means that x is positive, y is positive, and z is positive. And so I'm still going to be integrating, again, in terms of my function z equals f of x and y, even if it's not written like that yet. And so my region D is going to be, well, my xy plane projection. So if I set z equal to 0, well then, what's it going to look like in the plane? Well, I'm going to have the line 2x plus 3y equals 9. And again, I'm bounded in the first octant, which also means I'm bounded in the first quadrant. And so I just get this triangle here in green. And that's my region D that I'm integrating over. So now let's take the time to set this up as either a type 1 or a type 2. Now, for a triangle like this, it really does not make a difference whether we set this up as a type 1 or a type 2. It's just a matter of preference. I'm going to set this up as a type 1, but you could absolutely set this up as a type 2 and get the same answer. So type 1, the first thing I need to do is bound x by my constants. And again, hopefully we can see in this picture that we're clearly bounded between 0 and 4.5, or 4.5, or 9/2, or however you want to write it. And again, we could just pretty quickly solve for the x-intercept given my original line. But then but the next step is to bound y by my functions. Now, hopefully we can pretty clearly see that y is going to be bounded below by 0, and then it's going to be bounded above by my line, 2x plus 3y equals 9, except I can't leave it like that. I need to solve it to be y equaling a function of x so that I can substitute later on. So if I take that equation of my line, 2x plus 3y equals 9, I need to solve it for y so that I get as a function of x, and that will be my upper bound. So y is going to be bounded between 0 and then negative 2/3 x plus 3. And again, make sure you're pausing the video, verify that yourself, do the algebra, make sure that you get the same bounds as I got. Now, the second step is, well, I need to find my partials. But before I can find my partials, I need to set this up as z equals a function of x and y. And that's not the case here because I have my x's, y's, and z's all together. So the first thing I'm going to need to do now is do some algebra so that I can get this z here by itself. So again, pause the video for a second, do the algebra, solve for z, get z equals, and then let's see if our answers match. Because I'm getting z equals 3/2 minus 1/3 x minus 1/2 y. Of course, when I simplify and reduce each of my fractions. Now that I have it written as my z equals format, now I need to find my partials. So I need to find the partial with respect to x and the partial with respect to y. Now this one, it's pretty straightforward that the partial with respect to x has got to just be negative 1/3. Now for my formula, I need my partials squared. So negative 1/3 squared is, well, negative 1/3 times negative 1/3, which is going to be positive 1/9. And then we need to do the same thing with the partial with respect to y. Well, the partial with respect to y is going to be negative 1/2, and negative 1/2 squared is positive 1/4. The third step is I'm going to plug my results into my radical and try to see if I can simplify it. Now, admittedly, this step is kind of optional. We could just jump in and actually plug everything into our big giant integral expression for the surface area and just see what happens there. I think it's a little bit easier to take some time and see if we can simplify now at this step while we have a smaller expression that doesn't have our double integrals and our dA everywhere. And if I do that, if I plug in and simplify now, well, again, replace the partials squared with what we found before, so that would be replacing it with the 1/9 and the 1/4. So plug that in, see if you can simplify that radical on your own. And then when you're ready, unpause the video. And yes, when I plug in those values and I do 1 plus 1/9 plus 1/4, I'm getting 49 over 36. And when I take the square root of 49 over 36, I just get the expression 7/6, which is kind of nice. It does simplify much nicer than if I just left it all the way it was written. So now I can jump to my fourth step, which is to actually plug it in and evaluate. So let's plug everything in now. So my surface area. So the first thing is, well, my bounds for x. So x is bounded between 0 and 4.5. Then my bounds for y between 0 and that negative 2/3 x plus 3. That whole square root expression simplified to just 7/6, and then of course dy dx, because I need to do this with respect to y first and then x second, since it was that type 1 integral. Except, wait a second, that 7/6, it's a constant. I can factor that out, which means that my integrand, the only thing I'm integrating is just 1. Well, that's my constant function. If you remember, if you're integrating the double integral over the constant function, that's just going to be the area of that region D that you're integrating over, or A of D. Well, we know what our region looked like. It was that triangle from before, right? Well, what would be easier? Finding the area of this triangle using, well, the formula for the area of the triangle, or would it be easier to find the area by taking a double integral? I'm pretty confident that finding the area of this triangle is going to be the much simpler way to calculate this. So the area of a triangle is 1/2 base times height. The base is at 4.5, or 9/2. The height is 3, and so 1/2 times 9/2 times 3 is really 27/4, which means we can bring that back to my problem. And I still have that 7/6. Don't forget that constant was factored out in front. So 7/6 times the area of my triangle 27/4, and my answer becomes just 63/8. Now, that's my answer. And again, hopefully we were able to follow, the calculus, the geometry, and the algebra that was all involved here. But this problem should also make a little bit of sense as well, because again, if I have a plane, that's a flat surface, and that flat surface is going to be intersecting everything at an angle. All right. Now, the area of that triangle normally was, of course, well, the 27/4. But when I angle it, I'm actually stretching it a little bit. And in this case, I'm stretching it by that factor of 7/6. So this is actually very much just a geometry problem to begin with. Now, again, play around with GeoGebra, see the 3D version, see if that doesn't make sense what I just said. If it doesn't, well, that's kind of okay too. As long as you can do the calculus, you should be fine. But again, there's typically reasons why we get the results that we do get. All right, let's do a second example. Let's try to determine the surface area of my function z equals xy bounded inside x squared plus y squared equals 1. So what I have up now is the actual surface z equals xy. And so we have kind of a saddle function going on. Clearly it's going down in one direction, going up in another direction. And again, feel free to play around in GeoGebra to take a look at what this saddle function really looks like. But what we're going to do is take that saddle function, and I want the surface area of that saddle function, except I'm bounding myself inside the cylinder now. So inside the cylinder, x squared plus y squared, I want to know the surface area just inside that region for my particular surface. Now again, there's nothing about it being positive or negative, so the surface area is going to be, well, the entire surface area inside that cylinder, even if it's below the x-axis, or I'm sorry, below the z-axis or above the z-axis. Now, the first step is, of course, to sketch our region. Now, in the xy plane, I'm bounded inside x squared plus y squared equals 1, and that's my unit circle. That needs to just be right there on the tip of your brain every time we see x squared plus y squared equals 1 when it gets to Calc 3. So I'm bounded inside my unit circle, and, well, clearly this probably means that polar coordinates might be easier, right? We know that setting up polar coordinates for the unit circle is really, really easy. My theta is bounded between 0 and 2 pi because I'm going all the way around the circle. And in this case, for my unit circle, well, it's bounded between a radius of 0 all the way out to a radius of 1. So my bounds are really nice if I set this up as a polar type integral. However, even though I can see at this point that polar coordinates will probably be easier and that I will probably be using them, we cannot convert until after our entire integral is already set up. So it's not until we actually can plug everything into my integral that I can actually start to convert. Because again, my surface area formula requires the z equals a function of x and y, which means I need to set it up with my function still written as z equals x and y. I can't introduce my r's and thetas until the very, very end when I actually go to integrate. But again, it is written as z equals a function of x and y, right? Z equals xy. So now I just need to find the partials and then square them. So the partial with respect to x, well, x times y is a constant. The derivative of x with respect to x is just 1. So I'm just left with my constant y, and of course y squared is, well, y squared. Similarly, in reverse, the partial with respect to y is going to be x, and then when I square that, I get x squared. The third step, like I said, I like to try to plug it into my radical and simplify first if I can, except there's nothing I can really do. I have 1 plus y squared plus x squared. There's really no simplifications I can do. I can just plug that straight in. Now, I do see a y squared plus x squared, which again is tending me to think that polar coordinates are definitely going to be the better way to go here. But it's not going to be until after I already plug all of these in and I get to this step right here that I'm actually going to try to go ahead and convert this to polar coordinates. So it's not until, again, I have my surface area integral. So the area of the surface is my double integral over the region D of the square root of 1 plus y squared plus x squared dA. And now I can convert to polar coordinates. Now, we do know that with polar coordinates, x squared plus y squared equals r squared. That is one of our fundamental substitutions that we can make. Now, of course, if you didn't remember that, we could do it the long way. X equals r cosine theta, y equals r sine theta. Plug those in, square them, factor the r squareds. That'll leave us with the sine squared plus cosine squared. We know that by the most important trig identity of them all, the Pythagorean trig identity, that sine squared plus cosine squared equals 1. And we get the same result anyway. But again, if we recognize that earlier, it can make life much, much easier. So when I make my substitutions now, again, like I said, that y squared plus x squared, I'm going to be able to replace that with r squared. And then with dA, don't forget, we need to replace that with r dr d theta. All right, do not forget that extra r there. That is a very common mistake that students make, and we do not want to make that mistake. Now, at this point, since I also switched to my r and my dr and my d theta, I also switched my bounds as well. So again, I'm doing this with respect to r first. So that is the bounds between 0 and 1. And then I'll do theta second, which is 0 to 2 pi. So how am I going to take this integral? How am I going to do it? Well, start with the easiest thing first, which is trying u sub. And u sub always means pick your inside function first. Well, my inside function is that 1 plus r squared. So that's my u. U equals 1 plus r squared. So du dr, because we're doing this with respect to r, make sure you're writing out your notation. Du dr is going to be 2r. And again, if I want to make my substitution, my u substitution here, with a little bit of algebra, I can see that 1/2 du is going to be my r dr. So I will be able to substitute that directly. When I substitute, let's also change my bounds of integration as well. So when r was 0, if I plug that in to my new expression for u, 1 plus 0 squared is just 1. And when I plug in my other bound 1, well, 1 plus 1 squared is just 2. So those give me my new bounds of integration. My 1/2, that constant, gets factored out in front of the entire thing. And so now I'm trying to integrate from 1 to 2 of u to the 1/2 du. Because again, it was under a square root, it was the square root of u. But if I want to take the antiderivative, or even the derivative, we need to write my radicals as my rational exponents, or my fraction exponents. So again, now I'm integrating u to the 1/2 du. This is just a straightforward application of the power rule. So we add 1 to my numerator. So 1/2 plus 1 is 3/2. Divide by 3/2, which is really multiplying by 2/3. And so there's my expression. Again, you should be doing this integral on your own, pausing the video as you need it. And so we can try to finish this problem now, and I'm going to bring the constants together. 1/2 and 2/3 is just 1/3. When I evaluate u to the 3/2 at 2, well, 2 to the 3/2 really doesn't simplify in any meaningful way, so I'll leave it as 2 to the 3/2. 1 to any power is, well, 1. So I get that expression. Now, the quantity, the expression, 2 to the 3/2 minus 1, but that's a constant. Those are all constants. I can factor that out from my limits of integration. And when I factor that out, well, now what's left under my integral is just 1. It's the constant function. And again, this is the constant function for a single variable, which means that when I integrate the constant function here, well, it's just the length of my interval. So the length from 0 to 2 pi is just 2 pi. So when I do 2 pi times my 1/3, I get 2 pi over 3. And then 2 to the 3 halves, well, that really simplifies to 2 square roots of 2. And then, of course, that minus 1 stays the same. And so there's my answer. That's my fully simplified answer. And again, hopefully we were able to follow. If you have questions, let me know. And hopefully that went okay. Now, the last thing I want to talk about in this video actually has nothing to do with surface area, but it's a concept that we should start to familiarize ourselves with now. And it's the question we haven't really asked yet, which is, what do I do if I want to evaluate indefinite integrals? So remember, indefinite integrals are the ones where we don't have bounds. They're the ones that I need a plus c at the end. And what happens if I want to take an indefinite integral of a function with two variables? Well, this problem I'm taking with respect to x. So I need to integrate term by term with respect to x. Well, the first one's not bad. What's the antiderivative of x squared? Well, we know how to do that one. That's 1/3 x cubed. When I take the antiderivative of e to the xy, we are going to have to do u sub for that one. And when I do u sub, my u equals xy. And again, if we do our u sub correctly, my answer ends up being 1/y e to the xy. And then the last one, y. Well, y is just a constant. It's a constant because I'm taking it with respect to x. So it would just be like 2. And what's the antiderivative of 2 with respect to x? Well, 2x. So what's the antiderivative of y with respect to x? yx or xy. And then, like I said, we always need to put a plus c at the end of our indefinite integrals. So I'm going to go term by term, and I get my antiderivative to look like this. But the question is, well, what does that plus c actually mean for a function of two variables? What is that plus c? Well, when we say plus c, that's a constant, right? But I also know that since I did this problem with respect to x, anything that's got a y is treated like a constant. So anything with y's is a constant, just like, well, numbers or constants, if I'm talking about with respect to x. So for example, and again, this is just an example, our constant, that means it could be any function of y. So just for example, if that plus c was really sine of y, well, if we go the other direction and check our answer by taking the derivative, what's the derivative of sine of y with respect to x? Well, 0. What's the derivative of any constant with respect to x? It's 0. And so I'm still going to get back to my original function with if I have my plus c being any function of y. And that's the idea, is that if I take an indefinite integral of any function of two variables with respect to just one of those variables, we still need to add our plus c like we usually do. It's just that that plus c is now a function of my opposite variable. So here's what it really looked like. So we took the antiderivative and we got my solution. 1/3 x cubed plus 1/y e to the xy plus xy plus c. That plus c term really becomes a function of my opposite variable. So since my original problem was with respect to x, that means my plus c is now a function of y, and some general function of y. And we typically use g's or h's to be our general functions. We try to avoid f's because again, most of the time our function f represents the function we're actually integrating with. But that's our solution, is that when I take my antiderivative, instead of that plus c, it has to be a plus a function of my opposite variable. And so that ends up being my solution. All right, so take some time to think about that last example and about what it means and about why it is the way it is. And like I said, it's a good idea to actually practice one time. Go through, take the derivative, check your antiderivative by, well, taking a derivative and see if that works. Also, of course, keep working on the surface area problems. It's going to be a really important part to things that come up in our next unit as well. So it's good that we're getting some experience with it now. And we will take another look a little bit more in depth later after we talk about some more advanced concepts that hopefully kind of tie it together. But as always, let me know if you have questions and good luck studying.